Hello friends, welcome back to Measure Theory lecture. This is our lecture number 4 and in this lecture we are going to see sigma algebra of sets and some example. Okay, so let's start with the definition of sigma algebra of sets. So first of all, let X be non-empty set. Now see subset of power set of X is said to be sigma algebra if it satisfies some conditions. Okay, algebra of X if it satisfies the following conditions. Okay, what are those conditions? The first condition is if a1 to ak and so on is a sequence in C, then their union is also there. Okay, so union I running from 1 to infinity also belongs to C. Yeah, and another thing is if A belongs to C, then A complement belongs to C. Okay, and third condition is X should belongs to C. Okay, so remember the definition of algebra of sets. Recall that definition and let's see that in that definition the only change is the condition number 1. Why? Because we have arbitrary union they here, but there we had a finite union which belongs to C, right? So in the definition of algebra of sets, we had that we have two sets that belongs to C and their union should be there. That means the finite union was there, and here we have arbitrary union. Okay, so you can observe a thing. You can observe that algebra of sets will belongs to sigma algebra, right? Why? Because we have arbitrary union here, and if we will take certain sets to be phi after a certain stage, then we can see it will become a finite union, right? If I will take all these terms to be phi, then it will become an just an finite union. Therefore always algebra will contain in the sigma algebra. Okay, so once more recall the definition of algebra generated by sets. Algebra generated by any subset of X. What was it? It was the minimum algebra that contained that subset, right? So same here, that sigma algebra generated by some set C is minimum sigma algebra that contains C. That contains C. Okay, so we have seen that this set is non-empty. Why? Because power set is always there, right? So power set of X will always contain C. Why? Because C is the subset of X. Okay, yeah, so we have here the definition of sigma algebra generated by some set, and we already know the definition of algebra generated by subset of X. So let's see some example here. So take n to be set of natural numbers. Okay, and C to be collection of singleton sets. Okay, now the question is find algebra and sigma algebra generated by C. Okay, so solution is okay. So from definition, first of all, we will find the algebra generated by C. Okay, so how will we find? So from the definition, we know the algebra generated by C is the smallest algebra that contains C. Okay, so the smallest algebra that contains C, that means C will be there. Okay, so we have some elements. What are those elements? If I will say the algebra generated by C to be uh, C of A, then what are some elements there? The C is already there. That means the singleton sets are already there. Okay, like 1, 2, 3, and so on. So all the singletons are there. Now from the property of algebra of sets, what we know is the finite union will also be there, right? So the finite union of these all singleton sets will be there. So I will write finite union of all singleton sets. Okay. So observe one thing, that the set of even numbers, I will write it on the next page, that set of even numbers does not belongs to C of A. Why? Because set of even number is what? This is 2, 4, 6, 8, and so on, which are infinite. And these infinite sets cannot be there. Why? Because we just have singleton sets right now. Okay. And we know that the finite union should be there. But this is our infinite union. Therefore, even numbers will not be there. Okay. So now let's come back to our problem. What we got, that the finite union of all singleton sets will be there, right? What does that mean? That means all the finite sets belongs to C of A. Okay, the algebra generated by A. Okay, so we got one thing, that the finite set should be there. Now another question is this the smallest or is this incomplete? This this is the smallest, but is this complete? No. Why? Because cofinite set also belongs to A, right? Why? Because we have just checked used one condition, right? That the finite union will be there. But what was another condition for to be the algebra of set? The another condition was that if A belongs to C of A, then A complement belongs to C of A, right? And what is complement of finite set? The complement of finite set is just cofinite set, right? So cofinite sets belongs to G of A. Now now we have completed all the possibilities, and now we have the set which contain finite sets and cofinite sets, and this is the minimum set, right? And what does that imply? That imply that C of A just contain finite and cofinite set. Okay, so that was the answer for the algebra generated by C. Now let's see the second part, that is sigma algebra generated by C. Generated by C. Okay, so what will be sigma algebra generated by C? We will just denote it using sigma A. Okay, so what do we know? We know all the singletons are there, right? Another thing is, what is the definition of sigma algebra of set? The definition is the arbitrary union should be there, right? If the sequence of numbers like a1 to ak and so on is there in C, then their arbitrary union is also there. So what we have is sequence 1, 2, 3, 4 and so on, right? And also what we have just mentioned previously, that the set of even numbers were not in the algebra generated by C, but here what we have is arbitrary union is allowed, right? Therefore we have the sequence 2, 4, 6, 8, 10, 12, 14 and so on. So their arbitrary union will also be there. Therefore even numbers belongs to C of sigma of A. Okay, not only even numbers, all the odd numbers will be there in the sigma algebra generated by C. Okay, so again notice a thing, let A to be any set that belongs to power set of n. Okay, so how will A look like? A will look like some elements like a1, a2 to an and so on. It will be either finite or infinite. So whatever this set will be, this can be written as union of some sequence, right? If we have, for example, if we have a equal to 1 2, then also we can write it as union of 1 and 2, just single set 1 and 2, right? This is our A. So the point is, any set A in the power set of n can be written as the arbitrary union of the elements of that set A, right? What does that imply? That implies that whole of power set is there in sigma algebra generated by C. Okay, what does that imply? That implies power set belongs to C of sigma algebra generated by C. Okay, so once the power set is there, this is the largest set, right? Therefore sigma algebra generated by C is power set of n. Remember, we were looking for the smallest such set that that will be sigma algebra, as well as that contains C also. Okay, so we have seen all the elements of power set are there, right? So if all the elements are there, that means whole of the power set is there, and there is no bigger set other than the power set there, and the smaller set than the power set will not be there. So the power set is the only set that is sigma algebra generated by C. So that was the example 1. Okay, so now let's see example number 2. Here let R to be set of real numbers and C to be collection of singleton sets. Okay, so the question is same. Find the algebra and sigma algebra generated by C. Question is find algebra and sigma algebra generated by C. Okay, so now first we will solve part 1, that is algebra generated by C. Okay, so once again what we have the collection of singleton sets, right? And we are allowed to take finite union there. So once again all the finite elements will be there. Take it as C of A. Now all the finite set belongs to there, and if once the finite set is there, cofinite set is also there. Okay, so just these two will belongs to there. Therefore, the sigma algebra generated by C will be set of finite and cofinite sets. Okay, so this is same. Algebra generated by C is same for real number as well as for natural number. Now we will move on to sigma algebra generated by C. Okay, so what will be sigma algebra generated by C in the case of R? So remember that in the case of natural numbers, what we had is we can write any set that belongs to power set of n as the a1, a2 means the form of singleton set. But here, if we will take any set that belongs to power set of real number, we cannot write it as in the form of singleton set, right? Therefore, what will happen is in the sigma algebra generated by C, power set of R will not be there. We are allowed to take arbitrary unions, but that is uncountable. Means if we will take any interval a to b, then there are uncountably infinitely many elements there, right? So I just can't write a point 00001 and a point it in the form of that set of singletons. Okay, and that's why we cannot write it as the arbitrary union. Therefore, just finite and cofinite set belongs to sigma algebra generated by C. Okay. Uh, do we have some other examples? No, I think. Okay, so see in this case, what we have is finite cofinite sets and countable set. So does countable set also belongs to sigma algebra generated by C? Yes. Why? Because countable sets can be written as a1 to an and so on. What are the countable sets? Countable sets are like q, right? Q, n. All these are countable sets. So these all sets can be written as in the form of this one. Means it's the more stronger condition than the finite set that there are countable sets And not only countable sets, if there are countable sets, then their complement will also be there. That means countable and co-countable sets belongs to sigma algebra generated by C. Okay, so that is the answer for our problem. And we don't have more examples, so thank you for watching this video. I hope you understand this.